Hello everybody, I hope everyone has been enjoying their SimFest 2021 online experience so far. In this talk, I'm presenting a framework, a design framework I have been working on for more than 1 year at this point, called Relational Joints Gameplay, Mapping How We Interact with Game Design. So, who am I? Well, my name is Simon Hoffiz. I am an architect with a master's in architectural design, a bachelor's in environmental design. I have 8+ years of experience in the industry, focusing mostly on hospitality. So I've designed hotels, master plans for resorts and Caribbean islands, water parks and restaurants, and so on. I also approach game design as a uh, as a hobby, but a very consistent endeavor on my part. I've been making freeware games since 2017 with an awesome online community called Home Team Game Dev, and I've done a bit of everything in these titles that I've personally helped to release. I've done programming, asset creation, animation, composed quite a bit of music for games, level design, and I've even led games. I'm also a professor of design of architecture at Kennesaw State University. So what is this framework aiming to do? Well, usually when we talk about, in this case, design, but in reality any type of design experience or interaction with a design, we usually think about them in a monolithic sense. And in the case of playing games, it is a very cool activity, but everybody does it at this point, right? Like everybody plays games, everybody has a game of some sort in their phones, and it just has become a very standard expectations of what humans can do. And we don't really think about it much until we actually start thinking about it. And either if we sit down with a friend or a game designer, or start on our own little journey of reading about game design or taking online courses and so on, that we quickly realize that this is a very complex activity. It's a very complex set of interactions, and just as fast as we tended to look at this as a very simplistic activity, it really pivots really fast into this like really overwhelming uh, sense of like I'm never going to be able to fully understand everything that is being taken into consideration and happening in this interaction, this design experience. So the relational joints model is helping us to be able to extract certain aspects, like the main components of a design experience, and relate them to each other in very specific ways, create a structure, place hierarchy, see dynamics, to be able to explain and talk and refer to this design experience that we were talking at the very beginning in a more nuanced and structured manner. So for the actual presentation, what are we doing? So I've divided this presentation into 3 parts. So we're first going to hit fundamentals, and then here we're talking about affordances and signifiers, we're talking about cognition, and we're talking about the flow state. Then and these are fundamentals, and I'm going to try to go as fast as I can explaining them, but I'm not going to sacrifice what I think is needed at a basic level uh, for me to explain, for you guys to have a very basic comprehension, because from the fundamentals is that the model, that second part of the presentation is generated, right? So in the model, we're going to see how we generate its individual parts, how we structure them, and the dynamics of how this framework help us model and visualize how we navigate and interact with design. And then we're going to go into different applications, both from an analytical standpoint and as a design tool. So let's get right to it. So affordances. Affordances was first coined for the psychology field by James J. Gibson in his book, The Ecological Approach to Visual Perception, where he states that affordances are every single possible action that a person can do with the object or environment in question. So let's say I present to you these two objects, and I ask you to tell me activities or actions that you can take on them. Well, we could say that, you can sit on a chair and you can throw a ball. Well, the term of affordances says that you can really also throw a chair and sit on the ball. And this is because the physical characteristics of the object in relation to our physical capabilities to manipulate that object or environment permits us, in this example, to be able to pick up the chair because it's not that heavy, and for us to be able to throw it, right? And in that case of the basketball is strong enough to uh, receive our weight and permit us to sit on it. So we could also say that, therefore, a chair affords being sit on, but it also affords being thrown, also affords being used as a ladder or as a desk. The ball affords being thrown, sit on, also affords being bounced or spinned, or being used as somewhat of a blunt weapon. Um, So then the term of affordances then was stretched into the design field by Don Norman in his book, The Design of Everyday Things, where he started to notice that certain affordances, like the form of the affordances of the object or environment in question, implied a specific function for the user. And that is why when I presented you with this case study of a chair and a basketball, your first actions that came to mind were sitting on a chair and throwing the basketball instead of like all the other, almost infinite possibilities of actions that can be taken with these two objects. And that's because, and this interpretation of how to use the objects, he coined, like Don Norman coined, as signifiers. And it's defined as characteristics of an object that stand out from a user's perspective that guide the user on how to interact with objects as the designer intended. Now, to make sure that we understand the differences of affordances and signifiers, but also how they work together, I'm going to use the case study of a door system so we can go through the analysis of it. So a door system affords the manipulation of its knob, the disengagement of its locking system, the panel rotation on axes, in this case the hinges, and passage through its frame. Let's say I present to you this door. And you know it's a door because we're talking about doors, but this object. And I ask you to tell me how this door is to be operated. Well, the most that you can reasonably tell me is, because of the seams on the wall, is where the door or the panel is actually located within the wall, and also the panel dimensions. Aside from that, you're not able to tell me where you should push or pull, or where the axis of rotation is in this door, right? Or even if there is an axis of rotation, it could be a sliding door for all that you know, right? You can never tell me with certainty that this door, that image to the left, is going to operate as the image to the right without first interacting with it, right? And this is because there are no design features. There are no signifiers, in this case of a door, knobs and handles, that are guiding the user on how to correctly operate the door. And as you can see with these 6 door hardwares, is that it becomes evident really fast how the door is to be operated depending on what hardware is on that door, and also how your hands are to be able to, or should, interact with that door hardware. And this is all because of the design features of the knobs and handles. And then this concept, or what this concept reflects, is that we have innate psychological leanings on how to interpret and operate the world, or the designs. And these psychological leanings, in this case, being reflected and being presented through the interaction with the door, was coined the Norman door, because Really Don Norman in his book was the one that really focused in on this, right? And just in this case, it's like, when we see a door, we see it with a plate on the door, we instantly know that, well, if we want to operate the door, we need to push it because there's really no where to actually grab it. In contrast, as if we see a grab bar, we grab it, and once that physical action, we have a psychological leaning to pull instead of push. And designers really should be understanding psychological leanings to better design. And what we really need to understand is that we are interacting with signifiers and affordances constantly throughout the days and throughout our lives. For example, in a coffee mug, the design is telling you in a very specific way how to and where to grab it when its contents are too hot. A mouse, which is telling you how to put your hand in a very specific manner on it to be able to successfully slide it across a horizontal surface. And even though it's a relatively very light object, it's not that comfortable to pick up. And of course, game controllers, where there's really only one evident, comfortable, and functional way where you can grab it and at the same time get to all the buttons to be able to operate the game. So up to this point, we've done affordances and signifiers in the physical space, but I really want to take it into the digital space, which is where the video games, the space in which video games actually live on. So for the case study of affordances and signifiers in the digital space, I'm going to use the hyperlink. And for that, well, the affordances of a hyperlink are it can be clicked and it gives you access to information via a tab, a new window, or a text box. The signifiers of a hyperlink are its underlying text, the different color from its context, and that the cursor changes when it's hovering. And these, at the very, very, very rudimentary level, are the foundational principles of UI design. But game spaces go a step further into the digital space. And at this point, I think it becomes important to actually define what type of games and what instances of games I mean when I use the word game space. So the first thing that we need to understand is that we're not talking about non-avatar games. So games like Candy Crush, where really the interaction and the way to operate the game are more akin to how a UI screen or interface operates rather than how the rest of the games operate. The other instance that we're not going to be referring to or including in our definition of game space is non-game world instances of the game, right? Like main menu, saving screens, inventory, all of that, which again function more like a UI screen rather than a game space. What we are going to be referring to are avatar-mediated games. It doesn't matter if it's 2D or 3D. And this is important because there is a very, very interesting mix of physical and digital affordances and signifiers that happen in these type of game spaces. So again, let's do a case study of how affordances and signifiers actually are reflected within the game space. And in this case, we're going into Mario's world, the classical first level, and we're going to analyze the block with the question mark. So the affordance of that block with the question mark is that it can be hit, on the underside to get a reward. The signifier is the actual question mark, right? Which is triggering the curiosity of the player to come and interact with this specific object. And these affordances and signifiers are also done in different ways and more modern ways too, right? For example, in the God of War games, we have non-diegetic elements like little UI icons that are floating on top of objects, in this case a chest, that the player can interact with. And we also have them in a diegetic sense, where it's the same language, the language within the world, be it music, environmental aspects, and so on, start to create their own language to guide and inform the player on how to interact with the world. In this case, the runes on that ledge are specifying that that particular section of that ledge can be interacted with, and in this case is climbing on it. And then there's something really interesting that happens in games like the Assassin's Creed and Watch Dogs franchises, where the developers and designers of these types of digital worlds are leaning on the player's parallel understanding of how to navigate the real world and bring that knowledge into their digital world to successfully navigate their world. For example, if you see in the real world a ledge on a building, well, you can reason that if you're fit enough to get to it, pull yourself over it, you've effectively climbed the building or part of it. And that's exactly how the Assassin's Creed's developers and designers want you to think to be able to navigate their world. And that's something really, really interesting. Okay, so the other thing that, now, and we're moving here into cognition, that we need to understand about affordances and signifiers is that for us to be able to interact with them, right, like interpret signifiers and operate affordances, we need what is called cognition, which is the amount of working memory that is being used to perform a task. Now, the amount of actual working memory we're going to be referring to, or it is referred to as cognitive load. Now, it is seldom the case where you only have a one-dimensional interaction or a very one level instance of interaction with any type of design to be able to successfully do the goal that you have with it. So this required or needed successful sequential interpretation of the signifiers and the execution of the affordances and their operations is what I'm going to be referring to as our cognitive flow. And it's important to understand that there are two instances where this cognitive flow gets modified. It is when something is not known, it is new, we're interacting with it and presented to it for the first time, where our cognition drops across time of interactions with it. And then when something doesn't work as expected, it's failing our expectations, which suddenly is requiring more cognition than what was expected. So let's use the piano, but or just learning whatever instrument or doing really whatever activity just for the very first time. Well, the first time that you're learning an instrument, in this case the piano, we all have this almost overwhelming sense of focus where we feel that we're putting everything that we have and that we are just to be able to keep up with the most rudimentary of fundamentals of that activity or that interaction. And that is because a higher rate of cognition, of cognitive load, is being used to be able to perform the task. And a way to explain this or to visualize it is that you're presenting your brain with a new challenge. And your brain does not know how to handle this. So it's going to, in the most efficient and effective manner that it can, try to resolve the problem as fast as it can. So it's going to take all that it has, all its cognition, all its cognitive load, it's just going to throw it against the wall, see what sticks, right? So the next time that you interact with it, it already now has an idea, oh wait, last time this and this type of cognition or this amount wasn't really needed, so I'm not going to reassign it this time. And so it goes through an iterative process as it is fine-tuning the actual amount of cognition needed, right? And that is why the second, third, fourth, 10th, 20th time that you've interacted with the piano, you can actually tell that what you're doing right now is not as difficult, doesn't feel as difficult or as big of an obstacle as it did that very first or second or third time that you interacted with the design, right? And you keep that idea, that iteration going down 20 years of interacting with the piano, and you get, your brain now needs very little cognition. And that's how you get people that are able to play Bach's and Mozart's masterpieces while also having a conversation. And this feeling of necessitating less and less and less amount of cognition to be able to interact more masterfully with the design more efficiently is what we feel as that sense of progression. And that's also how you kind of explain the one-man band phenomena, where you have a person that can barely play an instrument versus one that plays 17 at the same time. And then this graph is just here to depict in a conceptual manner, but visually, what we were talking about, right? So we can understand the requirement of the cognitive flow, the cognitive amount, in terms of cognitive amount and then interactions across time with that design. The more, at the very first start, we need a lot of cognition, whatever that is for each person. And then the more interactions we give the brain to fine-tune that amount that is needed to optimally interact and operate the design, it lowers and lowers and lowers until it just plateaus. And a very good example about this is doors. Everyone knows how to operate a door, and we could say we're masters at them, right? We've been doing this for decades now. Probably if you're seeing this presentation, at least, you know, for a decade and a half, you've been operating doors, and it is to the point where we do it constantly throughout the day, and we don't even think about it. It's almost as if it doesn't register anymore, right? And that's a pretty good way to identify how that plateau at the end of that cognitive modification, as it goes down and down and down and down and down throughout interactions, actually feels, where we actually need, the brain has figured out that optimal minimal cognitive requirement to operate a specific design. But we have all encountered this type of door, a glass door with the same handles on both sides, and every single person has gone through this horrible experience where the door does not operate how you thought it should. And it doesn't matter if, as you were approaching the door, you were texting with your mom, talking with a friend beside you, drinking coffee all at the same time, and you know, you thought, hey, I'm doing 3 things at the same time, I'm having no trouble, I've done this door thing a million times at this point in my life, I think I can handle it. You go, you try, you fail. And then in those, instantly you feel a sense of focus, again an overwhelming focus that goes into this door not working as you expected, right? You forget about the phone, about the friend, about the rest of the world, and the only thing in focus is the door. You know, your brain starts rushing, you know, is it closed, is it broken, and then suddenly you intuitively try to pull because you're pushing, and it opens, right? And you publicly redeemed yourself, so, you know, kudos for that. But even though that episode was instantaneous, you know, a couple of seconds at the most, it is still very memorable and palpable. And that is because a cognitive spike has happened because a design did not work as expected. And then this is the visual, conceptual graphic of how it would work. So once we get to that plateau of cognition needed to operate that specific design, when we have that spike, right? When we have that spike, it feels very noticeable in our brains. Okay, so, and now we go into the flow state. This is a very well-known concept in the game design circle, so I'm going to try to explain it as fast as I can. So the flow state was coined or created by for the psychology field by Mihaly Csikszentmihalyi in his book Flow: The Psychology of Optimal Experience, where he presents the flow state as the optimal state of mind when performing a task. And this is the holy grail, the top of the mountain that every designer, not just game designers in my opinion, should be after. So flow states understands a task in relation to 2 parameters or 2 axes. Challenge being presented to, or level of the challenge being presented to the user, and the skill level of the user to meet that challenge. So what happens if the skill level is far greater than the challenge being presented? Well, it creates a boring experience. Or we could also understand that as requiring very, very, very low cognition, just like opening a door. Opening a door is not a challenge to us anymore, cognitively speaking, but for my 2-year-old, it's still a challenge. It's still very interesting. He still plays a lot with it. But what happens if the reverse is manifesting itself, right? If the challenge is too great for the current skill level of the user, anxiety happens. And this could also be understood as very high amount of cognition being required to be able to operate the design. And what we really, or what the flow state presents, is that the challenge really should be located in between these two axes, right? Where we're completely engaging the user without overwhelming them. And that's where the flow state is created. And that's where the happy flow state is created, which we could also interpret or understand as requiring just the right amount of cognition. Okay, so we're done with the fundamentals. Let's move on to the model, to the relational pathway. Okay, so the first thing that we need to understand is that every user, when interacting with a design, is after a goal. That could be making toast, making a phone call, or playing a game for entertainment. This interface that happens with the design, right, when you're physically and cognitively engaging the design, this interface that happens, I'm going to be representing with this red dot. And all of this interface, right, requires cognition because we're interpreting signifiers and looking how to operate its affordances. And this interface requiring cognition, it's what I'm coining a relational joint. And the line that goes from the user to the goal, in which the red dot is on, I'm calling a relational pathway. Now, with those two concepts, let's build a relational pathway of making toast. So the first interface that happens is between the user and the toaster. The second one is between the toaster and the bread. So we have a relational pathway with two relational joints. Okay, in that first relational joint between the user and the toaster, the user needs to interpret the signifiers and operate the affordances of the toaster in the sense of the buttons and the levers, the proper handling of the toaster, how to plug it for power, and the correct orientation. On that second relational joint between the toaster and the bread, the user needs to understand how the platform lowers the bread, that there are metal coils inside the toaster are going to toast the bread, there's going to be an auditory signal, and the bread is going to be eventually ejected. And all of that is requiring cognition. So this is what the relational pathway model, or the RPM, for making toast looks like. A relational pathway with two relational joints. One from user to toaster, a second one from toaster to bread. Now, let's do the same exercise, but for an actual game. And, well, the first interface, that first relational joint, is between the user and the controller, in which the user needs to understand how to properly hold that controller and how to push the buttons. The second relational joint is between the controller and the avatar, in which the player needs to understand how the controller maps the actions to the avatar, right? X is jumping or dashing. Then the avatar to the environment, and again, the user needs to understand the interactions that happen between them. Can I destroy a brick block, or can I go down a green pipe? And then between the world and the actual goal is the final relational joint in this relational pathway, in which the user now needs to also understand how these two interact. If I hit that block, does a coin come out of it? And then this is the relational pathway model, or an RPM, of a game, right? We have from user to controller, controller to avatar, avatar to environment, environment to goal. So something that becomes quickly evident is that there's a specific sequence to this structure. when you're actually performing this design, not just analyzing it as a third person. And it is because the user cannot manipulate or understand how the avatar interacts with the environment if they don't first understand how to successfully operate and understand how to interface the controller, how to grab it in the most rudimentary and fundamental sense. Uh, and there's just no jiggling around this order. It really is a very specific sequential manner in which they have to be ordered. We also have a very specific taxonomy of categories where for this relational pathway, we can start grouping the first two relational joints as relating more to interfaces where systems are communicating, and the last two more around mechanics. And then the last thing is how this framework, this RPM, is helping us to visualize and model how we navigate and perform a design. In this case, it's really on a nature of loop and slide, so it's a very dynamic process. For example, when the user is first picking up the controller and it's figuring out how to grab it, how to put their hands to reach all of the buttons and all of that, the user is looping through that first relational joint and inputting the required cognition to be able to successfully navigate it. Once the player looks at the screen and starts using the controller to move the avatar, now it has slid to the second relational joint, and now it's looping through those two relational joints to successfully operate that instance of the design that they're inhabiting. And the same goes on, and it's really a very dynamic process that goes on. Okay, so that is the basic of the model. Now we're going to go into its applications, both analytical and as design tools. So the first thing that becomes evident is that we have a different way to compare design experiences against each other, where we can see that a game has 4 relational joints and all of that is implied, versus a making toast, which has 2 relational joints. But not just comparing design types, also instances of the design can be now taken apart and contrasted. For example, the main menu or the saving screen of a game has 3 relational joints versus the actual game space, which has 4. The other thing that this RPM, this relational joints framework, is helping us to do is to start developing a method for more accurate and holistic cognition measurement for the design experience. And here I want to be careful and intellectually honest and say that I'm really going to coin this as articulation, or at the moment of calling it and referring to it as articulation, meaning if a relational pathway has more relational joints in it, it is more articulated than one that has less. And why is this? Because I haven't done the experiments required to actually prove that is the case, that a relational joint with more relational a relational pathway with more relational joints in it has a higher overall cognitive load than one that has less. It could be reasonably deduced, and I think it's fine that we work on that premise. And I think this concept in general is really important because we have a limited capacity of cognitive load or information handling at any given time, and that's been proven to be 110 bits of information per second. And if we go beyond that, we are just creating a negative experience. We're overwhelming the player. The other thing is actual cognitive distribution analysis or resource allocation, which is a more nuanced approach to the cognitive measurement. And for this, here again is the game space RPM. We are going to do a little exercise, narrative exercise, to to depict the importance of this tool. So let's say that for this exercise, we're going to have 5 cognitive units represented by a circle, which we're going to be putting around the red dots. And again, when we're trying to create an experience, a design experience, we're looking to not go over or under in cognition, but rather create that flow state. So, okay, so we have the RPM, so we have 5 cognitive units, so let's get to it. So let's say we are hearing on a studio call, or the development of a game that is going out throughout the months. But as they start working on the game, well, the first thing that we need to understand is that there is some minimum cognitive requirement to be able to from the user to be able to interact with the controller. So we need to allocate that, right? So we put 1 there. So then the team starts really getting into the weeds of, you know, what type of controller they should have and how should it interact and all of that. So the first thing, again, we need to apply that minimum requirement. So we do. And then as we hear the team talking, they ended up saying that they were going to design their own new controller. And that is fantastic. It gets green-lighted by the studio. Everyone's really excited, but that comes at a cost, a cognitive cost in this case. So we add that second unit because more cognition is going to be required to be able to navigate through that relational joint by the user. Then the studio gets to design, gets into designing that avatar environment interaction. Again, we have to account for that minimal requirement. And someone has a really brilliant idea of this new way that the avatar is going to interact with the environment. Everybody loves it. It gets accepted. Again, more cognition is going to be required at that point. Then the team starts designing how the goal is going to be embedded in the environment and so on, but there is no more cognition. At the point where the player has to engage this part of the design, this instance of the relational pathway, the flow state is non-existent anymore. So, and again, like, this is really a loop of slides, so it's a really dynamic experience. So in this case, we're playing Mario, as you're navigating, and let's say we're having the relational pathway that we just depicted before. As the player is controlling the avatar and interacting with the environment through the controller, they might find it a little overwhelming, but not too much. It's fine. They're able to handle it. But for some reason, once they get to to hitting the block to get the coin, it doesn't feel right anymore, right? That doesn't mean that if you go past this cognitive threshold, it means that the user's brain is going to explode. I'm not pretending that that's the case, but it is where the overall sense of the experience gets twisted a little bit, gets tainted. Okay, so here let's use this from an analytical tool, which we were addressing it as, to showcase it, to more of a design tool. So someone that is approaching a design with this type of framework in mind would use it in this way. So the first thing is that once we figure out all the actual relational pathway and all the relational joints specific for the game instance that we're designing and analyzing, we need to apply and understand that there's going to be a minimal requirement across all relational joints, minimal requirement of cognition. So we account for that. And then we start getting into the design part. And if now we understand that if we're going to be designing a new control, or we're going to be redefining and restating the conventions of the industry of X is to jump and the start button is to bring up the inventory menu and stuff like that, we need to understand that there's going to be a higher requirement of cognition for the user in those first 2 relational joints, which, if you remember, are centered more around interfaces, systems communicating with each other. So that means that a guiding principle now for us as designers of this game is that the rest of the game needs to be lighter in that requirement and cognition. So we're not really trying to break or innovate in the game in that area of the design. Let's say we're doing the opposite, where we want to come up with a new genre or a really new interesting mechanic. Well, that means that the last two relational joints, the one that are centered more around mechanics, are going to require higher cognition than normal. So that means that we really shouldn't be messing around with any new controller designers or changing controller schemes and all of that. And again, this is where the taxonomy of categories and this added language really comes in handy to talk about a design instance in more detail. Okay, the other thing that becomes really helpful in having this monolithic design experience broken down into its main parts is that now we can have the idea of putting specific actual real cognitive requirement amounts to each of those relational joints, and that helps us to generate a mathematical curve which is starting to represent and depict and categorize a general design experience, and that really becomes helpful in our talking about and analyzing design experiences. Because from the nuanced analysis, we can now start making general categorizations that are a little more accurate and reflect reality. And for example, in that first curve in the top left, we have a curve that starts low and then comes up, becomes steep. Well, that is really akin to the known sense of a game increasing in complexity and skill, where the fundamental interactions of a game, like the controllers and how they work, are really easy to get, and the complexity really comes from the emergent sense of the mechanics. But if we have the reversed curve, where it starts really steep and then goes down, we can also reflect that as, and this is a phenomena that happens a lot in board games, is where the player first needs to understand the complete system, needs to understand all the thousands of pieces, what they're for, where they should be, when they're going to be used, before even attempting a rudimentary state of gameplay. Another one is if we have a flat but tall curve. It could be said that that game is taxing in all its instances and it's just overwhelming. That's too much going on. But if we have the inverse, a flat low curve, well, there's nothing really interesting going on. It's underwhelming. It's boring. It's like, you don't find anything interesting about opening 1,000 doors in real life anymore, right? Another aspect is where it's starting to have, this model, this framework is setting the ground for us to be able to start harnessing different type of design tools, in this case, the cognitive spike. So because we have the whole design experience broken down and defined into its pieces, structured in a way, we can now start identifying, like, okay, that cognitive spike, where in what relational joint should it happen? How much should it be, or for how long should we maintain that cognition modification? And this is all with the goal of avoiding frustration. So what is the minimal of all of this that avoids the frustration part of the cognitive spike, but help us to harness the focus aspect of it? And then the last thing is that because we have all these individual parts structured in a certain way, we can now directly relate them to each other and now understand that one relational joint is closer to one and it's farther to another, and we can start understanding and getting a sense and scale of how each one affects the other. And this concept I'm calling joint sections. And it's just the idea that we can now focus on each relational joint and see all the design instances that only happen or happen for the majority of the part in that specific relational joint at that specific instance of the design experience. Okay, so at this point, I'm going to make a case for why the camera should have its own relational joint. And up to this point, I've been trying to maintain the relational joint as simple, relational pathway model as simple as I can, just because I'm introducing the concept. But I think up to this point, we're well into it. So I think the camera should have its own relational joint because it moves independently and interacts with the environment independently. It has a different set of capabilities and functions, and has overall an independent set of rules, interactions, and roles. And I'm placing the camera in a parallel with the avatar connected to the controller because it gets manipulated by the controller, like both avatar and camera. And they interact with each other, and they also interact with the environment. So again, going back into the joint sections, I'm gonna give like 2 to 3 examples of each one, so we get a sense, like a sample platter of the usage of having the capacity to identify specific design instances for each relational joint. So for example, in the user controller case, design concerns about ergonomics happen here, right? Is a controller supposed to be functional and comfortable, or is it more a showpiece where function is really not the end goal? Also focus. As you can see in the right image, Star Fox for the Wii had the user's attention focus really split into the controller and the TV or the big screen, and equally valid information was being offered to the player to be able to win the game, where they needed to constantly be dividing their focus versus like the most conventional way where we're really expecting the user to just visually not focus on the controller to be able to play the game. If we move to the control camera, we have design instances of like scope. How much of the world am I showing the player? How much of the world am I letting them take in? Can I see enemies coming from afar, and can I prepare for them? Versus if I'm given really limited amount of information but really focused, but a lot of control of the camera. What's the overall scope? Also the position of the camera with the avatar. If the camera is really far away from the avatar, and the avatar is just this little humanoid servant, it's like, whatever it does, it's just a tool, right? It died, well, that hammer. But versus if the camera is positioned right to the back of the avatar, now the player is getting a more personal, emotional tie to the avatar's viewpoint and how the avatar is supposed to be experiencing the game world. Then controller avatar, we have design considerations like control action mapping, right? Is X jumping or slashing the sword? Also, dexterity versus complexity. Am I expecting my players to be able to push 17 buttons in less than 5 seconds to be able to do a basic combo? Or, is this just a really laid-back click and drag game? Then we have the avatar environment, where, is the world a linear world or an open world? Also general interactions with the world. I'm able to open portals on the walls, slash big cubes, stick to the walls, swim. And then finally, environment goal. Perceived casuality. Like, is the lever that I'm pushing in this corner of the building, and it's opening the gate at the other end of the building, when I do that, is there like a direct, causation that it's being registered by the player, either because the game has been designed to create a direct side of line to the gate opening, or there's a cutscene, as the action being directly related to the goal. Also area of scope, like how much area are you going to make your player have to consider to interact with a problem and get the goal. And then this is just a a bit more of examples that go into each relational joint that further the concept of relational joints. So in the user control, we have design requirements of ergonomics, key configuration, intended use, input feedback, required focus. From control avatar, we have failing expectations, action mapping, required dexterity, lack of feedback, and focus. Avatar environment, action possibility, interaction fidelity, expectations, action cohesion, and glitches. And environment goal, we have complexity, perceived casuality, glitches, etc. And then finally, I think the biggest thing, the biggest development that the relational joints framework is helping not just the game design field, but I think the design field in general, is that, well, at the moment when we talk about design, yes, we definitely have clear ideas of individual components and how to design them. We have clear ideas of how that component relates to other components, right? Uh, and we know that there are some design instances and elements that matter more at the start of the game than at the end, and vice versa. But we don't really have a complete, cohesive picture of how everything ends up interacting and relating. And I understand that this is a really complex problem with different vantage points that it could be viewed from. So this is, I'm not saying that this is the answer to all of our problems, but I'm just saying I think it's a more accurate uh, tool to be able to talk about design experiences. And right now, the way that I visualize how we have and talk about design experiences is like this graph right here. And the relational joints pathway, uh, it's really helping to structure this a little bit more. It's putting hierarchy, it's putting order, it's relating specific parts of the design with each other. And then I also want to stress that the relational joints framework is not saying that the framework, the relational pathway that I have presented here today, is the one for all games. In reality, this is a system that's offering us set of rules and understanding to create a relational pathway for each game. Yes, there are going to be some generalizations, maybe based on genres and so on, but each game, when analyzed, should be thought of as a new relational pathway to be generated. And also a step further to that is like different types of designs are going to necessitate different types of relational pathways, right? It's not the same playing a game versus making toast. And that is it for this presentation. I hope you have enjoyed it. I'm really excited about this concept. There's a lot more that just because of time I haven't been able to include here. But if you want to reach out to me to talk about this, share your ideas, get to know me more, collaborate in a sense. I'm always looking for that next project. Please reach me at my portfolio site, simonhoffiz.com. There's, in the contact page there, you just, you can write the email. It'll send it directly to me, and I'll reply happily, and we can engage in a conversation there. But yeah, that's it for me today. So thanks for your time, for attending my presentation, and I hope you keep enjoying your SimFest 2021 experience.